Okay, so today we're going to be working some example problems having to do with steady state sinusoidal power analysis. So for our first problem, let's say that we have the following circuit. Where we have a 120 volt, or excuse me, 120 angle 0 degrees volts RMS source. Some impedance ZA, some impedance ZB, some impedance ZC, and then we have current source that is 5 angle 45 degrees amps RMS. So, and let's say that ZA is equal to 10 plus J8 ohms. ZB is equal to 12 minus J3 ohms. And ZC is equal to 8 angle 30 degrees ohms. We want to determine let's see, average power absorbed by impedance ZA, the apparent power absorbed by impedance ZB, the reactive power absorbed by impedance ZC, and finally the power factor for the voltage source and the power factor at which our current source is supplying power. So, how do we go about analyzing this circuit? Anyone have any thoughts? Or what can we easily figure out right now? The average power for element A? Yeah. Okay. How might we go about doing that? We could. There are 2 nodes for which we don't know the voltage, so we'd wind up having to get out a computer and use MathCAD. So I'm gonna write out some quantities here. All right. So for our impedance ZA, I am arbitrarily going to choose that it has some RMS phasor voltage VA having this polarity and an RMS phasor current IA having this direction. I'm going to do something similar for VB. And IB. And something similar for VC. And IC. So these are the quantities that we're going to wind up using for parts A, B, and C. for our power factor for our voltage source and the power factor for our current source. I'll do those in a different color. This is the voltage for our voltage source. And since we want the power factor at which it supplies, I want my current flowing into the negative polarity terminal. So this is going to be IVS. And let's say this guy over here is VCS, which makes this guy ICS. So what do we know by inspection out of all of these quantities? Okay, so we know that ICS is exactly equal to 5 angle 45 degrees amps RMS. Okay, I agree with that. We obviously know that VVS is equal to 120 angle 0 degrees volts RMS. Do we know anything else? Okay, so IC is negative ICS. So that means we're gonna either add or subtract, it does not matter, 180 degrees to the angle of ICS in order to get rid of that negative magnitude. So that would look like 5 angle negative 135 degrees amps RMS. So I would argue that since we know the current flowing through impedance ZC, we actually have all the information that we need to figure out the complex power being absorbed by ZC, right? We could, if we were so inclined, find the voltage, but it's really not necessary. So we can knock out part C pretty easily here, right? So we know, and I don't have my notes from last time handy, so I will derive it super quickly. The complex power S is SC is going to be VC times IC conjugate, which is going to look like the magnitude of IC squared times ZC, right? So that would be 5 amps RMS quantity squared times 8 angle 30 degrees ohms. Excuse me, let me find my calculator here. So 5 squared times 8 angle 30, 25 times 8, so it's going to be 200 angle 30. Should have been able to do that in my head. 200 angle 30 degrees volt amperes, which is the same as 173.205 plus J 100 volt amperes. Since we're trying to find the reactive power, it's just this guy right here, right? It would be the imaginary portion of the rectangular representation of the complex power. So we could say that QC is 100 bar. anything seem unreasonable about the analysis that we did there. All right, so we've gotten this guy taken care of. What's next? Scroll back up to the circuit diagram here. So we need to figure out what VA is or what IA is. We need to figure out what VB is or what IB is. Then we need to figure out what IVS is and VCS is. So how do you propose we go about doing that? So using KVL is how I would get the answer at the end, but it would require me knowing some other voltages first. So let's focus on parts A and parts B here. All right, so the voltage and or current flowing through impedance ZA and the voltage and or current flowing through impedance ZB. I, looking at this guy, would approach it as a superposition problem. And the reason why I say that is if I do with my voltage source on and my current source off, I can easily figure out what VA and VB is just using voltage division. And with my current source on and my voltage source off, I can easily figure out what that VA and VB is as well, just using Ohm's law, because I know how much current is going to wind up flowing through that combination of impedances, right? So using superposition, let's say voltage source on and current source off, my circuit's going to look like this guy, right? So I'll have 120 angle 0 degrees, volts RMS. Here's ZA. Here's ZB. Here's ZC. Because my current source is off, I replace it with an open circuit. Here is VA prime. Here is VB prime. I would argue I could find either of those quantities trivially using voltage division, right? So VA prime is going to be 120 angle 0 degrees, volts RMS. So let's see, VA, or ZA was 10 plus J8. So I'm going to have 10 plus J8 ohms in my numerator, and then 10 plus J8 plus 12 minus J3. And that's going to give me 68.115 with an angle of 25.856 degrees volts RMS. And then VB prime, I could do voltage division again but I'm not going to. I can say that VB prime is 120 angle 0 degrees VRMS minus VA prime. And that's going to give me 65.791 angle negative 26.841 degrees volts RMS. Does that analysis seem reasonable? With my voltage source off and my current source on, what I have is a short circuit here. ZA. ZB. C. This guy's 5 angle 45 degrees amps RMS. And so this is going to be VB double prime. This is going to be VA double prime. And I can observe by inspection right now that VA double prime is just negative VB double prime or vice versa, right? Those two elements are in parallel, but the polarity of the voltages that we're looking for are opposite. So VB double prime to me looks like 5 angle 45 degrees amps RMS multiplied by ZA times ZB over ZA plus ZB, because we know that all of that current is going to flow through element ZC, and then it's going to flow through that parallel combination of ZA and ZB. So that would be 10 plus J8 times 12 minus J3 over 10 plus J8 plus 12 minus J3. And so I get let's see here, VB double prime to be 35.106 with an angle of negative 123.181 degrees volts RMS. And again, VA double prime is just negative VB double prime. So that would be 35.106 with an angle of I made a mistake in my notes here, and I just left it with the same phase angle, but that's not true. So I need to add, let's see, negative 123.181 plus 180. So positive 56.819 degrees. And this would be volts RMS. Finally, now VA is just going to be VA prime plus VA double prime. So that's going to be 68.115 angle 25.856 plus 35.106 angle 56.819 or 99.865 with an angle of 36.276 degrees volts RMS, which in turn allows us to do SA is going to be magnitude of VA over ZA conjugate, excuse me, the magnitude of VA squared over ZA conjugate. So that's going to be 99.865 squared divided by 10 minus J8, which looks like 778.762, angle 38.660, or in rectangular form, 608.111 plus J 486.489. Amperes. Since we are trying to find the average power, PA is just the real part of this, so that would be 608.111 watts. Catching what I'm throwing thus far. So we would determine VB in the exact same way. It's just going to be VB prime plus VB double prime. Let's see, what do we have here? 65.791 with an angle of negative 26.841. Plus 35.106 with an angle of negative 123.181. So VB is 71.069 with an angle of negative 56.244 degrees. It's RMS. And then obviously the complex power absorbed by element B. Let's see, what are we trying to find here? The apparent power. All right. So that's still just going to be the magnitude of VB squared over ZB conjugate, or 71.069 volts RMS quantity squared over, now we'd have 12 plus J3 ohms gives me 408.333, an angle of negative 14.036 degrees, volt amperes. Since we're looking for apparent power, we just take the magnitude of the polar form. And so SB is 408.333 amperes. So I'm going to scroll up real quick and I want to put some check marks by what we know at this point. We know VA, we know VB, we know IC, obviously we know ICS, and we know VVS. So the two quantities that we have left to determine in order to solve this thing, so the last thing that we need to do is determine our power factor at which our voltage source and current source are supplying. So the last two pieces of information that we need are the current flowing through the voltage source and the voltage drop over the current source. So let's start with the current flowing through the voltage source. How can we determine that based on what we know?
So for ZA and the voltage across ZA.
Right. So we know the voltage across element A, and we know that IA and IVS represent the exact same quantity because it's the current in series through those elements. So IVS is VA over ZA. So that would be 99.865 angle 36.276 degrees volts RMS divided by 10 plus J8 ohms. Which I get to be 7.798 with an angle of negative 2.384 degrees amps RMS. So our power factor at which our voltage source is supplying power is going to be cosine of the angle at which the voltage source operates, which was 0 degrees, minus the angle at which the current flowing through the voltage source, which is minus negative 2.384 degrees. So that's going to be cosine of positive 2.384 degrees, or 0.99913. Is this voltage source operating at a leading power factor or a lagging power factor? Why do you say that it's leading? So when we have a positive angle, or so I guess the better, what quantity is positive? I mean, you just said the word positive, so what are you thinking when you say the word positive? Okay, so the power factor is the numerical value is positive. So since we're calculating supplied power, all that means is that that source is actually supplying because it has a positive value. If it had a negative value, that means that source would be acting as a load or it'd be absorbing power. So that's not particularly helpful. So whenever the angle of theta S, which is by definition theta V minus theta I, is positive, and what I mean by positive there is between 0 and positive 180 degrees, then our power factor is lagging. If the angle is negative, so between negative 180 degrees and 0, the power factor is leading. And I believe we talked about that in the last class. All right, so now let's take a look back at our circuit diagram again. And figured this guy out. So the only thing that we have left to figure out is that quantity VCS. Any thoughts on how we might do that based on what we know? KVL. Okay, so Ms. Broussard, tell me what my KVL equation is going to look like.
Negative VB plus VC plus VCS.
Is equal to 0. Okay, so I'm going to rearrange that in my head and say that VCS is going to be VB minus VC, right? Where C is simply IC times ZC, because we never actually bothered figuring out what that voltage VC was. So VCS is equal to VB minus IC ZC. So that is going to be 71.069 angle negative 56.244 degrees volts RMS minus, sorry, this should be 5 angle negative 135 degrees amps RMS, I believe, times 8 angle 30. And I get that to be 53.875, angle of negative 22.308 degrees volts RMS. And so from this, the power factor at which our current source is supplying power is going to be cosine of negative 22.308 degrees minus the current flowing through the current source. The negative polarity terminal has an angle of positive 45 degrees, if I'm not mistaken. So cosine negative 22.308 minus 45, 0.385778. So our current source is operating at a much lower efficiency than our voltage source. So it seems to be the one that's supplying most of the VARs to the system. Is this power factor leading or lagging? It'll be leading because negative 22.308 minus 45 is a negative number. Yeah. How do you guys feel about that? Pretty okay. That's about really as hard as I can make these kind of things and have you, well, I mean, I guess since you're going to be allowed to use your computer, I could be a total jerk and give you something awful, but I'm not interested in doing it because I'm not interested in grading it. So I feel like that one was relatively straightforward. There was a number of different ways that we could have done things, obviously, but I tried to keep the analysis kind of on track and efficient as possible. So we only have about 40 minutes remaining. So I think I'm going to kind of combine two of these example problems here. So let's say that we have the following circuit. So in this system, we have some voltage source, which could be the single phase of the transformer, that is feeding 3 loads, and the transmission line that is being used to connect the voltage source to the loads has some impedance. So let's say that our impedance for our transmission line is 0.1 plus J 0.2 ohms. Let's say that load number 1 is absorbing 30 kilowatts at a power factor of 0.8 leading. Let's say that load number 2 is absorbing 20 kVA at a power factor of 0.9 lagging. And let's say that load number 3 is absorbing 10 kilowatts at a power factor of 0.8 lagging. And we are told that the voltage drop across our loads is 480 volts with with a phase angle of 0 degrees, volts RMS. We want to find that source voltage based on the information that we're given. We want to find the power factor at which the voltage source is operating. And we want to find what type of capacitor or what size of capacitor would need to be connected in parallel with our voltage source to raise the power factor to unity. So any thoughts here? Okay, so let's define some things. So I can say that there is going to be some voltage drop, VW, across my transmission line impedance. There may also be, or there will be, some current IW flowing through my transmission line impedance. And then that current will split among the different loads. That same current is the current flowing through my voltage source. So it looks like, to answer part A, we are going to need to figure out, so I would argue that if we knew that voltage VW, we could write a simple KVL equation to figure out what VS is. To get VW, we're going to need to figure out what IW is. So any thoughts on calculating IW?
The current through each of the loads and add them together.
Okay, so that is definitely one approach. How would we go about doing that?
Use what we know from each of the loads and I guess write it down and use the voltage and try to figure it out from there.
Okay, so that's a reasonable place to start. So we know a few different things about each of these different loads, okay? For example, for load number 1, that 30 kilowatts, what does that represent? The average power, the reactive power, or the apparent power? The average power. It's given in watts, so it's the average power, okay? So we know the average power absorbed by load 1. We know the apparent power absorbed by load 2. We know the average power absorbed by load 3. We know the power factor at which all 3 of them are operating. What can we determine using those pieces of information? In a roundabout way, yes. So I would argue that we have enough information to find the complex power absorbed by each of those three loads. And then from that, knowing the voltage also, we could work backwards to calculate the current flowing through each of the loads, right? So let's look at load 1 specifically. I'm going to call this S1. So the relationship that we are going to be using here is really just the definition of power factor, right? Power factor is defined as the ratio of the average power to the apparent power, and that it's also cosine of the power factor angle, theta S, right? So we could manipulate this guy and say that S, our apparent power, when we're not given it, is simply P divided by our power factor. And theta S, which we also aren't given, is simply the inverse cosine of our power factor. And so now probably seems fairly obvious that we have enough information to calculate all of these complex powers pretty trivially. So for the complex power absorbed by load 1, that would be 30 kilowatts divided by 0.8 with an angle of inverse cosine 0.8. So before we do this calculation here, I want to point something out. The fact that we have leading and lagging is important here, all right? So whenever we have a leading power factor, we know that our angle should be negative. But when we do the inverse cosine of any of these numbers, we are going to get a positive angle. So specifically, when we have a leading power factor, we need to force the angle to be negative by including a negative sign there. So 30 over 0.8. With an angle that is the negative inverse cosine of 0.8, I get 37.5 with an angle of negative 36.870 degrees kilovolt amperes. The complex power absorbed by load 2. How are we going to do that?
It gives us the like absolute or the magnitude of the complex power.
Right, so we're already given the magnitude, so we should not be dividing by the power factor in this case because we already know the magnitude explicitly. It's given to us as 20 kVA, right? So we would just have 20 kVA with an angle of inverse cosine 0.9. And because our power factor is lagging, we do not need to include a negative sign before the inverse cosine. So that's going to be 20 angle inverse cosine of 0.9 or 20 angle 25.842 degrees kVA. And then the complex power absorbed by load 3 is going to be 10 kilowatts divided by 0.8, angle positive inverse cosine 0.8, or 12.5 angle 36.870 degrees AVA. So the original suggestion was that we could find the current flowing through the three loads, through each of the three loads, and then use Kirchhoff's current law, add those currents together, and that would give us IW, which is also IVS. There's nothing wrong with that at all, but I usually just add the powers together and then find the current flowing through the composite load, because that is the current flowing through the transmission line itself. So it's doing the steps in the opposite order. Instead of finding the currents and adding them together, finding the currents from the power and then adding the currents together, I'm adding all the powers and then finding the currents that flows through everything at once. So our total power then, I'm going to call this S comp for the composite load, is just S1 plus S2 plus S3. Which gives me 58.339 angle negative 6.182 degrees kilovolt amperes. So now that I know the total amount of complex power absorbed by those three loads, how do I go about solving for my current? Yeah, so S is equal to V, which we know, times I conjugate, which we're trying to figure out. So I would argue then that I conjugate is S over V, or I is S over V conjugate. Does that make sense? So we had this guy originally, right? What happens if we conjugate the left-hand side? So what if we double conjugate something? We get the original value. So if we conjugate the left-hand side, to get rid of the conjugate sign, we have to conjugate the right-hand side as well. So I'm going to call this guy IW. The S in this case is the total complex power. So that's going to be 58.339 angle positive 6.182 degrees kilovolt amperes, because I'm conjugating my numerator. And then my denominator here is going to be 480 angle, and I'm going to list it as -0 degrees, even though I know it doesn't remotely matter. just to remind you that you are supposed to perform the conjugate operation on the denominator as well. I get a current, of 121.540 angle 6.182 degrees amps RMS. So I think we are ready now to say Vs is equal to IW times ZW plus V composite, which is that 480 angle 0 that we were given at the beginning. So that's just Kirchhoff's voltage law around the loop, right? So Vs will be equal to VW plus this 480 angle 0 degrees. So 121.540 angle 6.182 degrees amps. 0.1 plus J 0.2 ohms plus 480 angle 0 degrees RMS. And let's see, so that is 490.128 angle 2.979 degrees volts. RMS. So we solved part A in a significant number of steps. Part B will be a little bit easier. All right. We want to find the power factor at which the voltage source is supplying power. That's easy enough, right? The power factor for our voltage source is going to be the cosine of the voltage. So that's that 2.97, the phase angle of the voltage, excuse me, 2.979 degrees minus the phase angle of the current flowing through the voltage source, which we know to be positive 6.182. Or 0.99844. It's going to be leading because the angle is negative. Now, for part C, we want to find the capacitor value. That will make this happen, right? So our equation to determine the capacitor value, or the one that I'm going to use here because we haven't explicitly figured out what any of the old power factor or anything is, although we could absolutely do that, is negative Q new minus Q old divided by omega VRMS squared. So one thing that I need to do then is know what omega is. So let's go way back up here at the beginning and say that our circuit is operating at a frequency of 60 hertz, because you can't determine omega from anything because we're working everything in the frequency domain, right? So I have to have provided that to you, and I forgot to do so because I was combining example problems and made a dumb mistake. So if we're operating at a linear frequency of 60 hertz, that means that omega is simply 2 pi f is going to be 120 pi radians per second. So that's what omega is. VRMS in this case is just the magnitude of our voltage Vs, right? Because, let's scroll back up here real quick. We are placing our capacitor in parallel with that voltage source Vs. So obviously the voltage drop across the capacitor, or the magnitude of the voltage drop across the capacitor, is just the magnitude of that voltage Vs. So we have two other things that we don't yet know, Q new and Q old. I would argue that we do know what Q new is. Since we're aiming for a power factor of 1, what does Q new have to be? 0, right? Because if the power factor is 1, that means that all of the apparent power is average power and none of the apparent power is any reactive power. So we know that this guy must be 0. So the last thing that we need is then that quantity Q old. How do you think we might be able to go about solving for that?
Maybe put the voltage source in rectangular form. And would that be cool?
So Q old is representative of the reactive power, so I'm not entirely sure how the real or imaginary part of the voltage would give us that directly. So in the last example problem that we worked, we found Q for element C or something like that, by determining the complex power and then looking at the imaginary portion. So Q old is the reactive power that's being supplied by our voltage source. So it stands to reason that if we can find the complex power supplied by our voltage source, the imaginary portion of that is the Q old that we're looking for, right? So S Vs. I think this might literally be the first time that we're actually using the definition of complex power in the original V times I conjugate form. So this is going to be Vs times I W conjugate, right? So that is going to be 490.128, angle of 2.979 degrees, volts RMS multiplied by our current, 21.540. Sorry, 121.540. Angle negative 6.182 degrees. Amps RMS, and I need to double check that real quick. Yeah, so IW had a value or an angle of 6.182. So when we conjugate it, we have negative 6.182. So let's multiply these two numbers together. So let's see, that's going to be B times the conjugate of what I have stored as A. 59,570.223 with an angle of negative 3.202 degrees. Volt amperes. And in rectangular form, that looks like crap. All right. So I'll tell you why I said crap in just 1 second. 59.477199 minus J 3327.804 volt amperes. I should have noticed a moment ago. The reason why I said crap is because the capacitor value that we're going to wind up getting is going to be negative. And the reason is that we're trying to use a capacitor to correct a leading power factor, but that will never work. Because when we add the capacitor to the system, if we add a positive capacitance to the system, it's just going to make the power factor even more leading. So it's going to move it further away from having a phase angle of 0, right? So because we have a system power factor that is leading, we would actually need to correct this with an inductor. That's never done in practice because you never actually have a leading power factor in practice. All those induction motors and all that kind of good stuff, your transmission lines, all that stuff wind up having leading power factors. Literally the only thing I can think of that would ever have a leading power factor would be something that uses a huge capacitance like a rail gun or something like that. So if you were trying to do the power distribution system on a naval attack vessel, then maybe you'll have to do correction with a large inductor bank. But the wildly overwhelming portion of the time, your power factor would have wound up, your system power factor or source power factor would have wound up being a lagging quantity, which would then require an inductor to correct it. So we can't actually compute a value for C here, or we can, but it'll just be negative. But the process that we've done is perfectly correct.
So if it's negative, do we just replace that with an inductor?
So we could, this equation is specifically, this guy right here is specifically for finding C, right? So we would actually have to derive a new equation for finding the inductor that would correct it, which isn't going to be particularly difficult by any stretch of the imagination. But you'll literally never use it except here in this example problem because I screwed up and gave us a system where the source is operating at a leading power factor. So process is correct. So parts A and B, perfectly reasonable. Part C bit me in the butt, but the process is there for how you would approach this in your homework problems and all that kind of good stuff. But obviously you can't correct a leading power factor with a capacitor because its whole job is to make the power factor more and more leading. All right, I think we're done for the day because we only have 3 minutes left, and apparently I'm embarrassing myself at this point. So you guys want to talk about anything else for the next 3 minutes, or are we good to get on out of here?
This is the revision part of circuit 1, right?
Yeah, review of circuits 1. For the most part, yeah. The only new material really that you've covered, or that we have covered, is how to handle multi-frequency circuits. Everything else is straight circuits 1. Yeah, so if you have multiple sources operating at different frequencies, that's the only thing that's remotely new. And it's just a simple extension of what you guys did in circuits 1 anyway. So after today's lecture, we'll get into 3-phase power, which will be, actually, that's not true. After today's lecture, we're going to do 2 lectures on filter circuits, which should be wholly new to you guys. But it is building upon the steady state sinusoidal analysis that we did in some respects. And then after those 2 lectures, we will get into 3-phase power, which is new, but it is overwhelmingly rooted in the steady state sinusoidal analysis that we've done. Like typically students seem to struggle with 3-phase analysis, and I think it's largely due to the jargon and has nothing to do with the actual circuit analysis whatsoever. Like once we get into 3-phase power, we have to pay attention to what are called phase quantities and line quantities. And it can be confusing what the difference between those quantities are, because sometimes they represent the exact same thing and other times they don't. And understanding when they're the same and when they're not is the hard part. The analysis is fairly trivial. Like the analysis of the 3-phase circuits, we're going to break them down in such a way that we're going to wind up with circuits that look like this. A voltage source. We have a transmission line impedance. We have a load impedance. Figure out voltages and currents. Like that basic single loop frequency domain circuit is what we're going to analyze 6 ways from Sunday. But getting the 3-phase circuit to look like that takes a little bit of effort. Once we learn how to do that, the analysis is a joke. Yeah, that's it. We're going to spend however many lectures I have said, that many on that. Yeah, so we got 2 more lectures for 2 lectures for filters, and then I don't know, 5 or 6 or something lectures for 3-phase power, where the first lecture is going to involve no math whatsoever. It is literally just going to be me trying to explain what the hell the difference is between phase quantities and line quantities. And then I have hope for you guys, but I usually wind up pretty disappointed 2 class periods later when I'm like, let's solve for this. And everybody's like, I don't know what the hell you're talking about. So we'll see. I got some very negative reviews one time when I had to review it 3 times in a row and got a little pissy about it. So just saying. All right, I'll see you guys on Thursday.